All right, welcome back to the back side of homework number, whatever number this is. I think it's 4. Homework number 4. So we're going to start with some binomial theorem questions, which I know is everyone's favorite, so get excited. I actually really do like binomial theorem, and if you guys have seen me working on that problem, I think that binomial theorem is actually the key to it, so I have to go home today and do some binomial theorem for myself, so you can do it with me. It'll be so exciting. Okay, good. So we're going to start with x plus 3 to the 5th power. Our step number 1 is writing out our blanks. So if we have 5 as our original exponent, we're going to do 5 plus 1 blanks. So 6 blanks. 1, 2, 3, 4, 5, 6. Good. Next step is looking at Pascal's triangle. I unfortunately don't have one in front of me, so I'm going to draw one super quick. I'll draw it down here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. What row am I on? 3, 4, 5. It's because I'm going to look at the 5th row, right? So 1, 5, 10, 10, 5, 1. 1, 2, 3, 4, 5, 6. Good. So I have 6 numbers. Coefficient that goes first. 1, 5, 10, 10, 5, 1. Good. So we can see all of my coefficients right there. 1, 5, 10, 10, 5, 1. Good. Next, I'm going to start with my first term. My first term in this case is x, so I'm going to start with x to my original exponent of 5, x to the 4th, decreasing by 1 as I go across, and ending with x to the 0 power. Next, I'm going to take my second term, which is 3, and I'm going to start with 3 to the 0, remembering that my exponents need to add up to my original. 5 plus 0 is 5. Then I'm going to go 3 to the 1, 3 to the 2, increasing by 1 each time I go up. Good. So now we finished our setup. Super exciting. And now I want to simplify. So I'm going to bring down all of my blanks. Very exciting. Okay, so here. We know that 3 to the 0 power equals 1 because anything to the 0 equals 1. 1 times 1 is 1. 1 times x to the 5th is x to the 5th. And that reminds me, I'm going to bring down all of my x terms right now so I don't forget because I do that a lot. So x to the 0 we know is going to equal 1, so I don't need an x in that blank. Good. So looking at this line, I have x to the 4th, but my terms that aren't variables, I have 5 times 3 to the 1st. 5 times 3 is 15. Here, I brought down my x to the 3rd, so I just have 10 times 3 to the 2nd. 3 squared is 9. 9 times 10 is 90. Here, I brought down my x squared, so I just have 3. That's a 3. 3 to the 3rd power times 10. 3 to the 3rd power is 3 times 3 is 9 times 3 is 27. 27 times 10 is 270. In this one, I have brought down my x, so I have 3 to the 4th times 5. 3 to the 4th is 81. 81 times 5 is 405. In this one, we just have 1 times 1 times 3 to the 5th. 3 to the 5th power is 243. So I'm just going to write it down here for clarity, but feel free to leave it in your blanks. So I have x to the 5th plus 15x to the 4th plus 90x to the 3rd plus 270x to the 2nd plus 405x plus 243. And that's my final answer. Woohoo! We just finished our first binomial theorem. Look at how much faster we can do it now than we used to do it. That's super exciting. Let's work on this one. This is a tricky one because, again, our first term has a coefficient and coefficient and a variable in it. So we have to the 3rd power as our original. So I'm going to draw out 3 plus 1, 4 blanks. Looking at the 3rd row of Pascal's triangle, 1, 3, 3, 1. I'm going to write those numbers in. Oops. Oh, wait. No, oops. This is actually right. Good. So 1, 3, 3, 1. Starting now with my first term. Remember when we're plugging in a term, it goes like this. So if I'm doing 3x to the 3rd, like for my first term, 3x to the 3rd is going to be 3 to the 3rd x to the 3rd. So I need to put the exponent on both my coefficient and my variable and count down like usual in the same way with both of them. So I have 1 down by 1 each time in my exponent. Good. Next, I need to look at my second term, which is 1. So I'm going to start with times 1 to the 0. Again, my exponents need to add up to my original, times 1 to the 1, 1 squared, and 1 to the 3rd. Bringing down each of these numbers, I'm going to bring down x to the 3rd first, just so I don't forget, plus x to the 2nd, x And x to the 0 we know is going to be 1, so we're not going to worry about that either. Good. So starting here, 1 to the 0 is 1, but we do have 3 to the third. 3 to the third is 27. So we have 27x cubed plus 3 times 3 squared times 1. So 3 squared is 9. 3 times 3 is 27. So we also have plus 27x squared, but we can't combine those, right? Those aren't like terms because x to the third can't be added to x to the second because that's a different number of variables. Here we have 3 times 3 to the 1 times 1 squared. 1 squared is 1. 3 times 3 is 9, so plus 9x. Here, 3 to the 0 power is 1. 1 times 1 times 1 to the third is just 1. So we have 27x cubed plus 27x squared plus 9x plus 1. Very nice. Moving on to the next problem. Again, if you still have any questions about binomial theorem, now is a really good time to ask because we are moving on after this. And it's also not a part of your project. So this is kind of your last chance to get practice with that one. So let's now talk about this geometric series. We go from 2 to 7, 24.5, 85.75. To find the common ratio, we're going to take our second term divided by our first term, so 7 over 2. You can leave it like that. 7 over 2 is also 3.5, which is 3.5. Which this one is in decimal form, so if you put 7 divided by 2 period in your calculator, it'll pop it out as a decimal, and you'll get 3.5. What is the 10th term? We haven't done geometric series yet, or sequences yet. So u to the n equals u1 r to the n minus 1. Remember that the minus 1 is in the exponent. So the 10th term is going to equal our first term, which is 2 times r, which we know is 3.5, to the n minus 1. We're looking for the 10th term, so 3.5 to the 10 minus 1, which is going to be 3.5 to the 9th. So 2 times 3.5 to the 9th, if we put that into our calculator, will give us 157,631, or 157,631. So this is our 10th term. I just kind of crossed over the 1, so we'll add that back in. 157,631. Good. See, don't they seem so much easier than they used to? This is just great. So ACT problems. Starting with the one on the left, we have the manager of a grocery store asks Kumar to construct a display consisting of 10 rows of cans stacked on top of each other. The manager wants the bottom row to have 25 cans, and each succeeding row to have 1 less can than the row below it. Part of 3 rows of the display is shown in the figure below. How many cans will be in the top row? So let's think about this. This one's a little tricky, but I know you guys can do it. So we know that the bottom row has 25 cans, and that each one above it is going to have 1 fewer, because that's bad grammar in this ACT question, bad ACT. 1 fewer can than the row below it. So we can kind of think of this bottom row as our first term. So our first term is going to give us 25. Our common difference is a -1 because we have 1 fewer can each time we go up. So next we know we either need un or n. So we know that there's going to be 10 rows, right? So n is 10. There's only 10 rows. Un, it's asking how many cans will be in the top row. That's asking how many cans or the value of the 10th row. So we don't know what our un is. So let's use our formula. Is this an arithmetic or a geometric sequence? It's an arithmetic sequence because we're subtracting 1 each time or adding a -1. So we're going to use this formula, un equals u1 plus n minus 1 times d. Our first term is 25. We know that n was 10 minus 1 times -1. So we have 25 plus 9 times -1, or 25 minus 9. 25 minus 9. I'm going to push that back up. 25 minus 9. Ooh, wow. I don't know if you guys could see that, but now I'm going to move it up. 25 minus 9 is 16. So we know that there's going to be 16 cans in the 10th row. And that's answer choice C, 16. I'm just going to leave this up for a quick second. I know you guys can pause it, but that was my bad for doing all of my work when you couldn't see it. That's not super helpful. And no one really wants to hear me talk without seeing what my pencil's doing. So I'm very sorry. But we know that there's going to be 16 cans. Again, if you have any questions, you can come in and talk to me or Miss Avra. Good. So this next one, a group of 25 cells triples in number every hour. At this rate, how many cells will be in the group at the end of the 5th hour? Okay, so this is really a little bit tricky. This is an exponential growth problem, which I've talked to a couple of you about this. So geometric sequences are exponential functions. So it's kind of nice because we can use like exponential functions to kind of understand the behavior of our geometric series. So let's set this up as a geometric sequence problem, and then I'll tell you why it's a little bit different. So a group of 25 cells. So our initial term is going to be 25, right? That's the number we're starting with. And our common ratio is going to be 3 because it triples every hour. And we're looking for how many cells will be in the group at the end of the 5th hour. So our n is going to be 5. So normally if we were doing this, we would use the formula un equals u1 times r to the n minus 1 because we're starting with our first term and we're looking for it after 5 hours. And we would just plug it in and go. This one's a little bit different. I don't know if you guys remember the toothpick problem that we did right after we learned geometric sequences and series. And there was a problem where we had a lot of confusion because we kind of had a 0 term, or where we start at the 0. And people were confused, like, oh, is that my first term? Is that my 0? Like, how does this work? This is a very similar setup, right? Because we think about it, when we start, we have 25 cells. In hour 1, we are going to have 75, right? So times 3. So we're actually not going to use the minus 1 because our first term is 25.